It's been an exceptionally dry summer, and that's resulted in nights that are really clear. It looks like tonight's going to be another one of those, and so it should be a good night to photograph stars. There's just one problem. There isn't going to be any night at all. Let me explain why.
One of my favorite weather websites is 7timer, and this is showing my location because not all astronomical sites are equal when it comes to Rayleigh scattering. So here's the Netherlands, and as you can see, the cloud amount tonight is pretty much full, and that's because, of course, I'm making an astronomy video. One of the things that I really like about this site was that it was designed by a high school student who I now believe is studying his PhD. And it's amazing the amount of data that it shows, not just the weather, but also comprehensive data. This is temperature all over the world, all based on satellite data. And what I want to look at here is atmospheric extinction, which gives a measure of the amount of scattering that we're going to see from aerosols. These are particles 5 microns across or smaller. And so looking at the world, the best places are the ones in blue. For example, if we look at the ultimate place in the world for astronomy, that would be the Andes, Chile, etc. And here we're seeing a score of 0.3 on this aerosol index that's being used. Other good places, basically temperate zones around the world and deserts. So we're seeing the Sahara, Southern Africa, Middle East. Australia normally looks a lot better than this, but they're having really large humidity at the moment. Western United States, and Mexico and Canada, Asia, and the one place that really stands out as the exception is Europe. There are very few places in Europe that consistently score low, comparable with the rest of the world, in terms of aerosols. So you're seeing a few spots here over Spain and France, but in the Netherlands, no such luck. And so this is one good site to look at the effects of aerosols. You can look at anywhere in the world for the weather and also get these images, which you can simply save and store somewhere on your hard drive. Another website that I really like is called Clear Outside. And Clear Outside gives you also a lot of weather information for several days in advance at things like cloud cover. What it also has is annual darkness. And you can see we've just reached that stage here where I am 52 degrees north, where we're starting to get a dark night again. Now, when I started recording this video months ago, we just reached this point where there was no dark night. There's a few artifacts in the data that look a little suspicious, these sudden jumps. But basically, you're seeing the whole 2 months in the middle of summer where there isn't any proper night at all. And here we're looking at the effects of altitude of the sun below the horizon. So the sun's above the horizon, this orange zone. Here we're looking at civil twilight, which is not very dark at all. Here is nautical twilight. So at the end of nautical twilight, it's pretty dark. And that's all we've got in the summer. It still gets darker as we go towards midnight, local midnight, but never completely dark. The darkest it gets is astronomical twilight when the sun is 18 degrees below the horizon. Now, I wanted to investigate this effect a little bit further. So I took a series of photographs of Polaris with the sun at altitudes from 8 degrees to 12 degrees below the horizon, really just to see the effect of twilight and see just how bad it is as I braced myself for this horrific 2 months with no proper dark night at all. It wasn't as bad as I thought it would be. This chart shows the field of view of Polaris, and I photographed this at several times during the night as the sun got lower and lower below the horizon. The first image had the sun just 8 degrees below the horizon, and as you can see, it's way too bright to show stars well. Waiting just 20 minutes took the sun 2 degrees lower, and this is a 6-second exposure at f4. Another 10 minutes, 11 degrees, and another 10 minutes, 12 degrees below the horizon. This is the end of nautical twilight, beginning of astronomical twilight, and this 6-second exposure at f4 shows a significant number of stars. And this is useful. This is a trade-off we often have trying to photograph things that are close to the sun, like comets. This is comet Neowise. It wasn't possible to take this picture during astronomical twilight, But deep into nautical twilight, before the comet got too low, it still gave a good picture. So overall, what's the effect? Although it depends on your location, latitude, aerosols, etc., this time-lapse shows the effect of decreasing solar altitude after sunset. And it's at the beginning of the summer, so it takes us through almost to full darkness, but we get stuck in astronomical twilight because that's as dark as it could get. The holy grail of time-lapse photography is to keep a uniform exposure or effective exposure as time goes on. I've deliberately not done that here, but instead only adjusted the camera settings as the sky got darker and annotated the time-lapse sequence so you can see the adjustment at the bottom of the screen. Finally, the sequence ends with this dark shot, almost as good as full darkness, but limited by light pollution. But that's perhaps a story for another day.